so rates of change are also called related rates. These are all changes with respect to time. So like with implicit differentiation, where y will always have a chain of dy dx because you're taking the derivative with respect to x. When you're taking the derivative with respect to time, every single variable will have a chain that'll be d, whatever letter you're dealing with, dt. The only one that wouldn't need a chain would be if you were taking the derivative of time, because since time is t, you'd have dt dt, which would be 1, which is like the fact that you don't take the derivative with respect to x. So, these first three are a little bit, they're not odd, but they're not super typical rate of change problems. The ones on the other pages are a little bit more standard what you'll see. But these pop up in the bookwork, so I like to make sure I cover them. So, first one, it says, assume that x and y are both differentiable functions. They want you to find the required values of dy dt or dx dt. Okay. So here they want you to find dy dt when x is 4, given that dx dt is 2. So you need to take the derivative. So I would distribute the 3 before you do that. And then take the derivative. So the derivative of y would be 1 and then dy dt. Here you're going to get 6x, and then you chain it. So you'll have dx dt minus 6 chain dx dt. And then you just have to plug in the information that they're giving you. So it says x is 4 and dx dt is 2, so then dy dt, got 6 times 4 times 2 minus 6 times 2. So then dy dt is 36. All right, second one. It says find dx dt when x is 13, given that dy dt is negative 3. Fine, so same thing, you want to take the derivative. So x squared, you'll have 2x dx dt minus 2y dy dt equals derivative of 49 is nothing. Then you plug in what you have. You've got 2, 13, this is what we're looking for, minus 2, we don't know that. You go, that's probably not great. So you have to figure out what y is, but you're looking for y in a specific moment in time. Specifically, you're looking for y when x is 13. So then you want to go back to your original function. So then you've got 13 squared minus y squared is going to be 49. So then you end up with y squared being 120. So then y is just going to be the square root of 120. Technically, it's plus or minus the square root of 120, but because they're not giving you more information here, I would just use the positive version for this time around. So that's what will go here. And then it's just a matter of solving for dx dt. So then subtract that, divide by 26, and you're looking at negative 3 root 120 over 13. And that would be your dx dt. You could break 120 down if you wanted and simplify the square root. I probably wouldn't bother, it doesn't seem to help for that one because you're not doing anything else with it. All right, third one, it says a point is moving along the graph of the given function such that dy dt is 2 centimeters per second. So notice here, because they're labeling within the problem, you need to make sure that you label your answer. Well, that's the x dt, sorry. It says find dy dt for the given value of x. So, same thing, you need to take the derivative. So here, we've got dy dt. You cannot do quotient rule because you have a constant on top. Okay, you just need to chain it through. So really, and I'm going to put it up here so I'm not scrunching. You have 3 times 2 plus x squared to the negative first, so you'll pull down and chain it through. So then you end up with negative 6x over 2 plus x squared squared dx dt, which is sort of centered, or you can put it on top. Because again, you have negative 3, and then you have this, the negative second, and then you chain it through. And then those two should make friends. And then same deal, you're just plugging in the information that they gave you. So x is 3, the x dt is 2 centimeters per second. You would throw that through your calculator. And then dy dt would be negative 36 over 121. And then since this was centimeters per second, you need to label this centimeters per second. Now we'll get into some of the more typical problems that you tend to see. I'll probably blow this up a little bit so I can see it better. All right, so for 4, they want you to find the rate of change of the distance between the origin and a moving point on the graph. Y equals x squared plus 3 if the x dt is 4 centimeters per second. Fine. So if you are looking for a rate of change for distance, that would be d dt. So that's what you're looking for. If you're looking for a rate of change for distance, that requires you to involve a formula that uses distance. A formula involving distance would be the distance formula. So here's your distance formula. It's the distance between the origin. So one of the x's and one of the y's are going to be 0, 0 from this origin, and a moving point on this graph. And you know dx dt is 4 centimeters per second. Because you have a dx dt, you don't have a dy dt, you want the whole thing to be in terms of x. So here you already have y in terms of x, which is good. And the other x can just stay x. So then here you'll have x minus origin. Technically, you can make either of these 0. Makes sense to make the back half 0 so that you don't have to distribute the negative. Plus y is x squared plus 3 minus 0 squared. Then you're going to have to take the derivative because that will get you the dd dt. So I would FOIL everything out. So here you're looking at x to the 4th plus 6x squared plus this one, so 7x squared plus 9, because the zeros will go away. And then you want to take your derivative, so this will be dd dt, which is what you're looking for. And then here you've got a half. You have this to the negative 1/2, meaning it's a square root on the bottom. And then you have to chain it through, so you'll have 4x cubed. And when you're chaining like that, you can attach the x dt to each of the terms if you want, or you can chain all the x's at once and put it back here. It honestly doesn't matter, you can do it however you want, okay? So then they're telling you that the x dt is 4 centimeters per second. So this is going to be 4. So then this is really 2. can distribute if you want, but you really don't have to. And then there is your working formula for the rate of change for distance. You can label it or not label it. I'm not super picky when it's a formula. If you had an X value where you would have plugged it in and made it a number, I would absolutely label it. Labeling it centimeters per second isn't hard or the end of the world, so I'd probably be tempted to do it. But if you choose not to and leave it like that, fine. Okay. Number 5, it says the radius of a circle is increasing at a rate of 5 centimeters per minute. Find the rate of change in area when R is 8 centimeters. Fine. So, it's the trick, or I don't know if it's a trick really, but one of the important things when it comes to these formulas is you need to make sure that you know how to properly label things. So you need to actually read them through and not just take a shot in the dark at what everything is, okay? So it says that the radius is increasing at a rate of 5 centimeters per minute. Anytime you have a per minute, that's a d something dt, okay? So since it's the radius doing it, that would be dr dt, because when you have radius, that's always r. So dr dt is the 5 centimeters per minute. You're looking for the change in area. Well, area is A. If you want the change in it, that's a rate of change, so that's a d something dt. So it would be area, so it's dA dt. You're looking for the rate of change in area when r is 8 centimeters. Fine. So now you need a formula involving circles and area, which, fingers crossed, you should know. So your area formula for a circle is pi r squared. And now you have to make a choice. It's not really a choice, but you have to figure something out. You have to figure out if you're allowed to plug in 8 before or after you take the derivative. If it's something that is changing, you cannot plug it in until after you've taken the derivative. Okay? If it's something that remains the same the entire time, then you can just plug the number in before you start doing the problem. Okay? But here, they told us that the radius is changing, so you can't plug in 8 now. You have to take the derivative first, and then you can plug in 8. Okay? So you'll take the derivative. So here you've got dA dt equals, here you have 2 pi r chain dr dt. And then you have all the information you need. Because you know what dr dt is, you know what r is, you're looking for dA dt, so then you just plug it in. So then dA dt, and you want to give me exact answers. Don't round pi and multiply and give me the decimal nonsense. So then this would be 80 pi. And then you have to label it. Okay, so since the radius was in centimeters per minute, you're dealing with centimeters and minutes. However, it's area. And area is always in square units. So then you have square centimeters per minute. You need to make sure that you watch the labeling, because if you do the labeling wrong, then that would render the problem wrong and you lose points for things like that. So make sure that you're very careful about labeling your area correctly. Okay? 6. So sand is pouring from a pipe at a rate of 18 cubic feet per second. If the falling sand forms a conical pile on the ground, whose altitude is always 1/5 the diameter of the base. How fast is the altitude increasing when the pile is 3 feet high? Fine. And here I actually gave you the formula. If you don't know the formulas that you need for the bookwork, they're located in the back of the textbook. Or lots of them are cones, write this down somewhere, or they're circles. If it's anything other than like a cone or a circle, like on the worksheets and on the quizzes and stuff, I give you the formulas. I don't assume that you know them off the top of your head. Okay, so if this is our formula, that means the three variables that I'm working with are V, R, and H. Those are the three you have to pick from. You can't randomly invent new ones. So it says sand is pouring from a pipe at a rate of 18 cubic feet per second. So this is a rate of change. You have to figure out which variable it's a rate of change for. And that's where you want to read the problem. So since it says it's cubic feet, between volume, radius, and height, the only thing that's measured in cubic anything is volume. So that's going to be dV dt. Okay. It says the sand forms a conical pile on the ground whose altitude is always 1/5 the diameter of the base. Okay, so altitude, with the letters I'm dealing with, is h, because altitude is height. So it's 1/5 the diameter. Well, diameter is not a choice. Radius is a choice, and the radius is twice the diameter. There's that. So then we know our height is 2/5 r. And you know that might be important. It says, how fast is the altitude increasing? So altitude is height, and they want to know how fast the height is changing, so that's the h dt. And you're looking for that at a specific moment in time, specifically at the point that the pile is 3 feet high. Fine. So then you want to look at the information that you have, because when you have more than one variable, and both of them are changing, if you don't have rates of change for all of them, or information on all of them, you don't want all of them in the problem, okay? So you have a rate of change for V, you're looking for a rate of change for H, you know nothing about how R is changing. All you know about R is this, right here, where you have H in terms of R. That means you need to get R out of the problem, okay? So instead of having it be H equals 2/5 R, you want to solve this for R, and divide by 2/5, multiply by 5/2, whatever. And R is 5/2 H. Because now what you can do is you can have V is going to be 1/3 pi R, which is 5/2 H, times H. Now you need to simplify it. Please don't try to take the derivative between H and H where you do product rule between H's. That's nonsense. Also, make sure that when you're taking that when you're simplifying, you remember to square the number before you multiply it by a third. So then you end up with 25 over 12, 25 over 4 times a third, pi, and then you have 1, 2, 3 H's. Okay, so that's our new formula that we're working with. And now you have to decide if you can plug in 3 before or after you take the derivative. Well, this says that the altitude is increasing, and we're looking for it at a specific moment in time. So because it's increasing, that means it's changing, which means 3 is not allowed to go in until after you've taken the derivative. So then here you've got dV dt, and you've got 25 over 12, times 3, because we're taking the derivative. So you've got 25 over 4, pi h squared dh dt. H is 3. And dV dt is 18. And then you just have to solve for dH dt. In as many steps as it takes you to not do it wrong. So you would divide by 25 over 4, divide by 9, divide by pi. dH dt ends up being 8 over 25. And you divide it by pi. So the pi, when you divide by it, needs to be on the bottom. You have to make sure that you're conscious about where pi belongs. If it belongs on the top, put it on the top. If it belongs on the bottom, put it on the bottom. If you waffle it in the middle and hope that I'll guess that you put it in the right spot, no. Make sure that you put it in the right spot. So this one, since we would have divided, it needs to live on the bottom. And then the only thing you have left to do is you have to label. Okay, so this was cubic feet per second. Height's not a cubic measurement. Height's just a regular measurement, so then it's just regular feet per second. And there's that one. All right, last set of problems. feet long is leaning against the wall of the house. The base of the ladder is pulled away from the wall at a rate of 4 feet per second. How fast is the top of the ladder moving down the wall when the base is 15 feet from the wall? Fine. So we have house, ladder, wall. So really what we're dealing with is this right triangle right here, okay? So the ladder is 25 feet long. Fine. The base of the ladder is being pulled away from the wall at a rate of 4 feet per second. So that's a this direction thing. I'm going to call this side x. So that means that the x dt is going to be 4 feet per second. We want to know how fast the top of the ladder is going down the wall. So we're looking for this rate of change. So I'm going to call this y. So we're looking for dy dt when the base is 15 feet from the wall. Fine. So what we have here is we have this right triangle, and we're dealing with side lengths. So when you deal with side lengths of a right triangle, you want to use the Pythagorean theorem. So I have x, y, and L. Realistically, you can pick whichever letters make you happy, since they didn't give you letters for this one. Those are the three I'm going with. So I would use those three for this one, but if you want to use different ones for the future, go ahead. So you've got x squared plus y squared is L squared. Fine. So before you take the derivative, you need to make some choices. You need to see if you can plug anything in before you take the derivative. Now here, the ladder is sliding down, well, away and down the wall. So this is changing. Plus, I don't know what the number is. This is changing. The ladder is not a rapidly growing and shrinking ladder as you're trying to plug things in, okay? So because the ladder is going to stay 25 feet until the end of time, plug it in before you take the derivative. Now I get lazy. I wouldn't bother to figure out what 25 squared actually is, because when you take the derivative, this is 0 anyway. And the less I have to pick up the calculator, the faster I tend to be. So now you want to take the derivative. So you've got 2x dx dt plus 2y dy dt equals nothing. Okay, so 2x is 15, dx dt is 4, plus 2, you go, I don't know why, that's probably not great. This is what I'm looking for. Well, so now you have to decide if you can figure out what y is at the moment in time when x is 15 and L is 25. You see, but I have this handy formula that will find y for you. So you've got 15 squared plus y squared is going to be 25 squared. And really, this is a 3, 4, 5 triangle, so y is going to be 20. Or manually solve it and figure out y is 20 that way. And everything is feet, so then this is going to be feet. So then this can be 20. And then you can solve for dy dt. So you want to figure out this, subtract it over, divide by 40. Dy dt is going to be -3. And then this was feet per second. This also needs to be feet per second because we have to label. And this is where you have to make sure that you're reading the problem, because they're asking you how fast the top of the ladder is moving down the wall. So they've already given it a direction. If you're telling me that the ladder is moving down the wall at a negative rate, that implies that it's going up the wall, which is not what you want. So you would drop the negative to actually answer the question. Okay, because they've already given it a direction. If they just ask how fast the top of the ladder is moving on the wall and didn't give it a direction, then you would want the negative root. Okay? But because they gave it a direction, you need to pitch the negative. Last one, it says, consider the triangle formed by the side of the house, the ladder, and the ground. Okay. Find the rate at which the area of the triangle is changing. So we're looking for dA dt. And the base of the ladder is 15 feet from the wall. If the base of the ladder is 15 feet from the wall, that means all the nonsense that we figured out up here applies. When you're using it in the future, though, you need to make sure that you remember that this was negative, and the negative will have to go back in when you use it, okay? So now we're dealing with the area of our triangle. This was L, this was X, and this is Y. So the area of your triangle, or the area of a triangle, is 1/2 base times height. And then you're just going to take the derivative of it, because it's changing, so you can't put in 20 or 15 now. And then that dAdt is what you're looking for. So dAdt equals, notice here, it's x times y, so it's a product, so you can do product rule, because it's still a thing. So you've got first, derivative of second, plus second, derivative of first, and you have all the information. So you've got 1/2, x was 15, dy/dt, we have 3, but remember it was negative 3, plus 1/2, we said y was 20. dx/dt is 4. You put it all together, you get dAdt is 35/2. And then you go, I'm done. When everybody looks at you and says, no, you're not, you didn't label. You need to make sure that you label it. So since this was regular feet per second that we're dealing with, this is area. Area would be square feet per second. I cannot emphasize enough how much you need to make sure that you watch your labeling when you're doing these problems. Okay, watch your labeling, make sure you label your pictures and label your information. It makes it way easier to do the problems. And that is rate of change.